Good morning, everyone. My name is Lee Pucker, and I'm the CEO of the Wireless Innovation Forum. I'd like to welcome you today to the third webinar in the Wireless Innovation Forum's new webinar series. Today's webinar is entitled The ADCs of SDR, Parameters, Design Considerations, and Implementations. Thank you all for joining us. Just a few slides to get things going, and then I'll turn it over to the presenters. Couple things. The slides presented during this webinar are going to be posted on the forum's website. If you go to the home page and click Tutorials and Resources, you'll be able to find the links there. So that way you can get access to the slides later. We have a satisfaction survey that we've prepared for the webinar. The address is here, and you'll also get a copy of this address in the thank you message that we send you later. We really appreciate your feedback in these surveys on the webinars that we're presenting. We provide, we're trying to make these as a valuable service to the community, and so any feedback that you can give us, which will help us to improve them, will be greatly appreciated. If you want to speak to me directly about the webinars or really about anything related to the Wireless Innovation Forum, please feel free to drop me an email. My email address is on the screen here, and you can work from there. A few directions on the interface. If you look at the interface that you have, there's a couple of ways that you can work with it. First key point to notice, there's a little double arrow line. If you click that, it minimizes and maximizes your control panel. That makes it so that you can see what's going on. There's two key areas within there. The audio mode, which allows you to control how you're communicating. And if you're having problems hearing, I encourage you to use the audio setup feature there to correct that. Audio pin allows us to identify who you are when you're talking. Right now, everyone's muted. However, during the question and answer session, you'll have the opportunity to ask questions either directly through the interface, or you can use the raise hand button, and at that point I can unmute your microphone so that you can ask the presenters a question. The presenters for this webinar have asked that if you do have questions, please go ahead and type them into the questions interface as we go, and we'll answer those along the way. So with that, I'd like to introduce today's presenters. The first presenter is Mark Reeves. He's Principal Applications Engineer at Intercell, where he supports high-speed data converter customers and participates in new product definition. Mark spent over 10 years working on a wide range of system and IC designs before moving into applications. And since that time, he spent 12 years focused on high-speed data converters and communication systems. Mark received his bachelor's in electrical engineering from Mississippi State University. Second presenter is Ed Kohler. Ed's Intercell Strategic Marketing Manager for high-speed data converters and ADC drivers. Edward spent his career designing high-speed ADCs and was one of the inventors of Intercell's femtocharge technology. He earned his bachelor's and master's degrees in electrical engineering at Michigan Technological University and University of Michigan, and his MBA from Yale University. And finally, Tudor Davies is the Director of Technology at Spectrum. And in this role, he defines the architecture of Spectrum's future products and projects. Tudor joined Spectrum in 1998 and successfully led teams to develop and deliver products that met complex customer requirements. Tudor holds a master's degree in electrical engineering from the Royal Military College of Canada and served for 20 years in the Canadian Navy as a combat systems engineer. Again, I remind you to go ahead and type questions along the way in the question window. And with that, I'm going to turn it over to Mark to begin the presentation.
All right, thanks, Lee, and welcome everybody. The design and application of software-defined radios is a huge topic, and so today we're going to focus just on the receive side, and we'll cover the following material. Let's see, actually, I think Ed is supposed to be the one showing his screen rather than me. Can you send that back to him for us, Lee? There we go.
My apologies.
That's all right. No problem. So basically today we want to cover an overview of software-defined radio, and then we'll cover some ADC fundamentals and basic specs, how ADC parameters impact your software-defined radio system design, and then we'll cover a small form factor real-world implementation. The transmitter is very similar. It will include a high-performance DAC. A lot of the same concepts will apply, but we're not going to directly address those today because we just won't have time to do that. Let's see now if we can go for the next page. Which for some reason is not cooperating. There we go. All right. Sorry about that. So let's start by looking at the United States frequency allocation chart. The RF spectrum is vast. Currently, it covers 8 decades of frequencies ranging from 3 kilohertz all the way out to 300 gigahertz. The amount of spectrum that's been allocated has been increasing over time, and some of these allocations change as various needs come and go. Some bands will be allocated, unallocated, and then reallocated. So then if you look around the world, the standards and the allocations vary all over the world. So it's not just a huge number of channels in the U.S., but it's everything else is different. So we need to have a receiver to perform frequency translation and channel filtering that will allow us to select only the desired frequency band or channel from all these this huge range of frequencies. So traditional receivers that would isolate those channels only cover a single channel and a limited number of bands, and that's because they're made with dedicated hardware for a specific signal or waveform. Even signals in adjacent bands may require multiple receivers, which means that your system has to be larger, it uses more power, weighs more. So software-defined radio is a different approach where digitizing the signal with an A to D converter allows you to move circuitry previously implemented in dedicated hardware into the digital domain. So ideally, an ADC could directly sample the signal right from the antenna, as I've shown here at the bottom left. Realistically, ADCs don't have infinite dynamic range and infinite input bandwidth. So you need additional components still, like amplifiers and mixers and filters, in order to make this work with an ADC. It's got to condition the signal first. So after the signal is digitized, the software can control the channel frequency, the bandwidth, the modulation format. So it gives you a lot more flexibility. Placing the ADC as close to the antenna as possible will give you the most flexibility, but you run into performance limitations there, so you have to make the right trade-offs to get the maximum benefit. So now let's make sure we're all on the same page and go over some basic ADC fundamentals and some key specs. So let's start with a basic illustration of analog to digital conversion. The ADC, or our analog to digital converter, will be controlled by a clock known as F-sample or FS, which sets the sampling interval. The sampling process will introduce side effects that will add noise or distortion to the input signal. So we measure that performance by its impact on noise, typically reported as the signal-to-noise ratio, or SNR, and distortion. And there's several components there: spurious free dynamic range, or SFDR, total harmonic distortion, or THD, and integral nonlinearity, or INL. And we'll go over these in more detail. The ADC will convert basically an infinite range of analog values into a limited number of digital output values. So there's going to be distortion because all the necessary digital output values don't exist for this infinite input range. Additionally, the ADC will have non-ideal performance, so even more distortion can be introduced. Noise is going to be another problem because the ADC will have a limited range from the largest signal down to its noise floor. So this example shows that we're going to take a noisy input signal, and we're going to use an anti-alias filter to remove the noise, the high-frequency information, and that will give us a nice sine wave. We'll digitize that with our 3-bit ADC, This 3-bit converter will have 2 to the 3rd, or 8 possible output values. Sometimes we call those codes. Each input clock will cause the analog input to be quantized into one of these 8 possible digital output codes. Now, any undesired input signals must be removed by the filter, and that's this high-frequency noise in this case, because otherwise that will also be digitized, and that would be aliasing, and we'll come back to that and talk about that in a little more detail in a few minutes. So ADCs, when we test them, are typically characterized with a single frequency sine wave input, and that would generate this large blue tone right here. We would call it the fundamental, or a tone, a signal. This sine wave test is the most difficult case because if instead you use a wideband signal with multiple frequencies, like a spread spectrum signal, that range of frequencies will tend to randomize any linearity errors in the ADC, and you'll get better results. It's also easier, or maybe we would say more consistent, to process a fast Fourier transform or an FFT result with a single sine wave input. So let's start with SNR, the signal-to-noise ratio, and that is the sum of all the power except for DC, and the fundamental, and the first 10 harmonics. And so that would be all of this red power here. And that typically would be measured in dB relative to full scale, dBFS, so the ADC's full scale output, or in dBc relative to the carrier, or our input signal level. An ADC's SNR is set primarily by 4 factors: quantization noise, which comes from the number of output bits; thermal noise, which comes from the ADC's input. The ADC will have higher order harmonics due to DNL errors, or just periodic errors in the output, and there will also be clock jitter noise. The first 3 are set by the ADC's design, and those are relatively fixed. It's important to know that the jitter noise is influenced by external factors, and those include the clock jitter, the input frequency, and the input amplitude. So next, let's look at the effects of jitter in a little more detail. Clock jitter is a variation or an uncertainty relative to an ideal clock. If there's an error in sample time caused by clock jitter, there'll be an error in the sampled voltage relative to the voltage at the expected sample time. This error will create a higher level of broadband noise at the ADC's output, which will reduce the SNR. For small signals, the ADC's thermal noise will determine the SNR, but as the signal input amplitude increases, noise due to clock jitter will increase and can determine the SNR. And this is going to be especially true for higher input frequencies. Jitter noise is independent of the sample rate, which is kind of counterintuitive, but only the input frequency's slew rate and the amount of jitter determine the jitter noise. And this is because the voltage error that's created by the jitter will be greater with a higher slew rate. And slew rate only increases with frequency, the input frequency, and the amplitude. So it's unrelated to the clock frequency. Now, jitter is important in software-defined radios because it can reduce the sensitivity of the receiver. If you have a large signal sampled too much jitter, it can raise the entire noise floor, and we'll show that in this illustration. So the plot on the left shows the desired small signal, right here in blue. It has enough SNR relative to the thermal noise so that we can recover it. The jitter noise and a large interfering signal are shown in red. So what's going to happen is as that large interfering signal here increases in amplitude, you can see the jitter noise comes right along with it and will start to cover the desired signal. So now if we raise the signal even higher for our interferer, our desired signal will be masked by the jitter noise as it increases above the thermal noise, and we will no longer be able to recover that signal. Clock jitter will also degrade the SNR of higher input frequencies, which will lead to lower dynamic range in applications where you directly sample the RF. So that's one of the trade-offs that you have to make, how high an input frequency you do want to sample. These negative effects of jitter noise on the sensitivity can be reduced by using a low jitter clock and an ADC with a low internal aperture jitter. In a traditional receiver, the interfering signal would be removed by a filter, but since SDR processes a wider range of frequencies, that's not practical, and you have to have more dynamic range to handle that, the wider amount of spectrum that you're digitizing. On the distortion side, THD, or total harmonic distortion, is the sum of the power in the first 10 harmonics relative to the fundamental signal power, and it's usually measured in dBc, or dB relative to this carrier power. The spurious free dynamic range, or SFDR, is the ratio between the largest input signal, or the desired signal, and the largest signal below that, or the largest spur. Now, generally, the SFDR is set by a harmonic of the fundamental. As you can see in this case, H2, or the second harmonic, is the largest signal other than the fundamental signal. But in the case where you interleave ADCs, that may not be true. So if the two ADCs that are interleaved do not match exactly, they'll create a fundamental image spur, which would be over here on the right-hand side. And that spur can be higher than the harmonics if you don't correct it by calibrating the ADC cores. So Intersil's ISLA 214P50 is an interleaved 500 megasample 14-bit ADC, and it provides automatic calibration that typically keeps that interleaving spur below minus 95 dBFS, so that it will not interfere with the desired signals. Another important aspect is the clock. Any signal on the ADC's clock input, and that includes noise or any spurious tones, will be convolved or mixed with the analog input signal at the ADC's output. Any spurs or non-harmonic content on the clock signal will appear around every analog input signal and may mask a small desired signal adjacent to a larger signal. The amplitude of the spurs will be constant relative to the input signal, each input signal actually. The spurs are always there, but until the input signal is large enough, they'll be masked by the noise floor. So here we can see in this plot, the top is our clock with the two little spurs beside it, maybe from a switching regulator. The bottom is the ADC input, so we have two large input signals and then a smaller desired signal here in red. Now after we sample this with the clock above, you'll see that the large signal has the same spurs on either side that we saw on the clock, and that's true here for the second large signal on the right as well. The spurs are small, they're approaching the noise floor. But the important thing to notice is that our desired signal in red is partially covered by the spur from the clock. So it's important that everything be very clean, that you don't have these kinds of spurs where they will degrade the system performance. Now, SINAD is or the signal to noise and distortion, is the sum of all the power except for DC and the fundamental, relative again to the signal power. So that's again in dBc. This SINAD is the ultimate measure of dynamic range. Really, it's the difference between the desired signal and every other signal except for DC. The effective number of bits, or ENOB, is derived from SINAD using the equation ENOB equals SINAD minus 1.76 divided by 6.02. I mentioned aliasing earlier. Let's talk about that in more detail. Unless a signal is in the frequency range from DC, or 0 hertz, to FS over 2, we cannot know the original analog input frequency at the ADC's output. And this was described by Nyquist when he said analog signals must be sampled at more than twice their highest frequency to completely recover the sampled information. Most sampling discussions center on signals from DC to FS over 2, also known as the first Nyquist zone, because every input to the ADC will appear in the first Nyquist zone at the ADC output. It's also easier to visualize a low-frequency signal that has many sampling points. Now, as you can see in this example, two very different input signals, the black and red trace, both line up with the ADC's sampling points and will generate the exact same sampled output. There are an infinite number of higher frequency signals where the sampling points will line up correctly, and all of these signals will alias to the lowest frequency signal at the ADC's output, shown by this red trace. The sample alignment relationship will happen periodically around every multiple of the sample rate fs. This is why it's important to remove any undesired signals that might alias onto our desired signal before sampling, because after you sample, you can no longer separate these signals. Now, you can take advantage of this by using subsampling. Subsampling uses aliasing to provide frequency translation of a higher frequency signal into the first Nyquist zone. Sometimes this is referred to as undersampling or bandpass sampling. In subsampling, the carrier frequency is greater than the Nyquist frequency. For example, in this case, with the sample rate of 100 megahertz, the first Nyquist zone is from DC to Fs over 2 here. Inputs at 8 megahertz or at 100 minus 8 or 92, 100 plus 8 or 108, and so on will all alias into the first Nyquist zone. And that's exactly what we saw in the previous slide with the red trace. Now, you use an anti-aliasing filter to select only the input that you desire. So you can actually use a bandpass filter and select a higher input frequency from one of the higher Nyquist zones and only allow that signal to be translated. Subsampling is commonly used in IF sampling receivers, but you need to check on high IF sampling to make sure that the ADC's data sheet for the values for SFDR and SNR versus input frequency are going to provide the performance you need up to the maximum input frequency for your application. You also need to make sure that the sample rate is high enough that the desired signal or band will fit in the single Nyquist zone completely. Now I'd like to introduce Ed Kohler, and Ed's going to talk about an alternative method of frequency translation, and then he'll talk about several different receiver architectures.
Thanks, Mark. So as we've seen, the basic function of receiver is to select and translate information from a high-frequency RF carrier to a low frequency that's more easily processed. At the low frequency, the receiver removes coded information by demodulating the transmitted signal. So we've just seen how subsampling can be used to translate signals from one frequency to another, but often the frequencies we're interested in receiving are too high to be accurately sampled. Even state-of-the-art ADCs show increased distortion and decreased SNR at very high input frequencies. So one very important element in today's receiver is a mixer. The mixer provides the frequency translation function in the receiver by multiplying its two inputs. When the RF input is mixed with the local oscillator, or LO, the output will include two signals, RF plus LO and RF minus LO. In an ideal mixer, that's all you'd see, but in the real world, you also see a little LO feed-through, which is just an attenuated version of the LO. So in this example, our RF signal is at 100 megahertz, and the local oscillator is at 110 megahertz. So our outputs would be at 10 and 210 megahertz. Typically, the information we're after is present in only one of these signals, so we can use a filter to remove the undesired frequency. Now, one complication is that additionally an RF signal at LO plus IF and LO minus IF both mix to the same IF. So one must be filtered in front of the mixer from the RF signal. So for example, an RF signal at 100 megahertz, as shown, mixes with 110 to create a 10 megahertz signal, but one at 120 megahertz would also mix with 110 to create another signal at 10 megahertz. So you have to make sure and filter that undesired RF off. So now let's look at several ways that ADCs can be applied in radio receivers. Now the first architecture we're going to look at is a super heterodyne or low IF receiver. This is very typical, and its characteristic is two mixers cascaded with demodulation performed digitally. Now, using the example shown here, we can walk through the architecture. So our channel at the antenna is 2.16 to 2.18 gigahertz, and this is selected using a bandpass filter. This is followed by a low noise amplifier and then mixed with an LO at 2 gigahertz to provide our IF from 160 to 180 megahertz. This is then bandpass filtered again and followed with another variable amplifier and mixed down with 150 megahertz to give us our output spectrum of 10 to 30 megahertz. Now, this is a well-understood architecture because it's been used since the early days of receivers when ADCs could not handle frequencies much above the bandwidth of interest. Because the signal chain has several levels of bandpass filtering, the architecture is very immune to blockers or interfering signals from neighboring bands. And since the demodulation is done digitally, it's essentially perfect. On the downside, it includes a higher bill of materials due to the multiple layers of filtering, gain, and mixing stages. This architecture traditionally has limited flexibility as well because the filters are essentially tuning the receiver to the desired band of interest in hardware. And finally, since we've mixed the signal so close to DC, the second harmonics of the lower frequency ranges in the band of interest end up being in band. Now, on the bright side, for the ADC, this architecture allows for a fairly low sample rate and a limited bandwidth. It also reduces the importance of clock jitter, reducing the complexity of the clocking implementation required to drive the ADC. On the other end of the architectural spectrum is the 0IF or ZIP receiver. It's also called direct conversion. In this configuration, the RF is directly down-converted by the quadrature demodulator, which is essentially two mixers where the LO has been shifted by 90 degrees. In this configuration, the output of the quad demod, or I and Q, is amplified and then low-pass filtered and then goes to the ADC. You need two channels of analog to digital conversion, and they usually sample at a rate of about 4 times the signal bandwidth. Or this is about twice the minimum Nyquist sample rate. Linearity requirements for the ADC in the ZIP receiver are typically high, as harmonics, just like the previous example, fall in band of your band of interest. This tends to be a low-cost architecture, but mismatch in the offset gain and phase between the I and Q signal paths, typically from the mixers and filters, can limit the receiver performance. Any mismatch there shows up as an increase in the image frequency and DC, because the RF frequency was mixed to DC. The final architecture that we'd like to highlight is more of a compromise. This is a high IF receiver, and it's similar to the super heterodyne receiver, except one stage of mixing, gain, and filtering is omitted, and the input at the ADC is at a much higher input frequency. This architecture takes advantage of digital demodulation, like the super het version, but it reduces cost by moving the extra stage of mixing and associated filters into the digital domain. This architecture does require a higher input bandwidth at the ADC, but this is generally not a problem for today's converters. So this architecture provides a good compromise for software-defined radio. Compared to direct conversion, the higher ADC input frequency followed by a digital quadrature demodulator offers improved performance, while omitting the second mixer from the super het reduces the amount of fixed analog circuitry. However, the architecture has two key challenges. First is clock jitter. Since the input frequency to the ADC is relatively high, low clock jitter is critical to get good SNR. Second is the linearity of the ADC. Typically, linearity of the sampler in the ADC declines with increasing input frequency, so it may be difficult to achieve the SFDR required for some communication standards at the high input frequencies. One solution to this is to use higher sample rate ADC with careful frequency planning to move harmonics out of the band of interest. And I'll show you how that works in the next slide. So with a little care, frequency planning can significantly improve the performance of your radio by moving harmonics from the input stages and the ADC out of the band of interest. So for instance, in the previous example, our input signal to the ADC was 160 to 180 megahertz. By definition, the second harmonic then would be 320 to 360, and the third harmonic would be at 480 to 540 megahertz. If we were to choose to sample that input frequency at 80 megasamples, or about 4 times the bandwidth, as shown in this plot, HD2 and HD3 both alias into our 20 megahertz channel. You can see that here with the red and green covering the blue channel. However, if we were to sample this at a much higher sample rate, say 210 megasamples, we not only increase the sample bandwidth, which now goes up to 105 megahertz, but we change the way our signal and its harmonics alias. In this case, the input signal now aliases from 30 to 50 megahertz, and HD2 aliases from 60 to 100 megahertz, and HD3 will alias from 90 to 150 megahertz. Since our Nyquist frequency is only 105 megahertz, the portion of the third harmonic that lies above 105, that would be 105 to 150, 45 megahertz of that HD3, fold around Nyquist and back down to 60 megahertz. So in this example, neither HD2 nor HD3 fall in our band of interest here. Now, many ADCs will spec distortion or SFDR excluding the second and third harmonic, and this is how you can take advantage of this. This spec, excluding second and third, is often 10 to 20 dB better than the SFDR spec. So for instance, the ISLA 214P50 that Mark mentioned earlier is spec'd to have a typical SFDR at 190 megahertz of 78 dBc. However, its SFDR excluding the second and third harmonic spec is actually 88 dBc. So in this case, we can gain 10 dB in linearity by careful frequency planning. So now I'd like to turn it over to Tudor Davies to describe one implementation of a high IF receiver.
Thanks, Ed. So far, we've covered the basics of analog to digital conversion and discussed some receiver architectures that you can use in an SDR. Now let's tie these together and talk about how your choice of ADC can impact the design and functionality of your SDR system. We'll also look at some trade-offs you need to consider in an SDR design. To start, let's relate some of the ADC specifications that Mark and Ed mentioned. Next slide, please. First, the noise. We've got a slide advance delay here. The noise limits the smallest signal that can be discerned once digitized. This drives your receiver sensitivity. Second, linearity translates to freedom from distortion, as distortion is generally caused by nonlinearities. Distortion can mask desired signals and prevent accurate recovery of signals. Lower distortion reduces the interaction between multiple signals and improves your dynamic range. You can filter out harmonics before the ADC if they occur in earlier stages, but once they're in the ADC, they may alias down into the band. Next, resolution sets the quantization noise and is expressed generally by the number of bits in the ADC. As other factors of noise, distortion, and distortion improve, resolution ultimately becomes the limiting factor in performance. The instantaneous dynamic range ties noise, linearity, and resolution together. It's the difference in signal strength between the strongest and weakest signals that you can successfully receive at the same time. Essentially, in dBs, is the maximum input level minus the noise and distortion level in the receiver. We call it instantaneous dynamic range because it excludes any variable gain, such as what we can get from variable gain control, such as or automatic gain control, or AGC. Dynamic range is critical for a wideband SDR receiver. In an SDR, you often want to digitize a wider bandwidth rather than, say, in legacy receivers where you might digitize only 25 kilohertz in VHF and UHF radios. With a wider bandwidth, there's a higher probability that you may have a strong interfering signal in band along with your desired signal. Dynamic range is also a key factor for multi-carrier receivers, as digitizing more signals at the same time requires that the input level for each signal be reduced to maintain the overall power incident on the ADC. So part of the price you pay for having the wide bandwidth is that you also need to have a wide dynamic range to accommodate the additional signals that appear within that bandwidth. Next, the sample rate. In general, a higher sample rate moves us closer to the ideal SDR, where, for example, you have the ADC connected directly to the antenna. It determines how much bandwidth can be digitized, allowing more flexible signal processing. A high sample rate enables flexible frequency planning by moving the aliases farther apart, including the aliases of the harmonic that Ed mentioned in his last slide. A high sample rate can also increase the SNR in the desired channel because you have some oversampling gain. In selecting an ADC, there's generally a trade-off between the maximum sampling rate that the ADC can achieve and its resolution. For example, Intersil's 14-bit ADC, which runs at 500 megasamples per second, is the fastest one currently available for a 14-bit resolution. Faster ADCs are available, but they generally have a resolution of 12 bits or less. So the trade-off, you go higher resolution, you don't go as high in speed. The amount of power that the ADC draws will also impact your SDR system performance. It affects battery life in portable applications, and it affects reliability as the higher power consumption results in a higher temperature, and the ADC is often one of the hotter components on your board. It also limits the number of ADCs that you can accommodate in high-density systems with multiple ADCs. There's a trade-off between dynamic range, sample rate, and power consumption. A higher dynamic range and sample rate also often mean a higher power consumption. Life's full of compromises. So now let's look at some design considerations at the system level. We like to call these care and feeding of high-speed ADCs. It's not too hard to get good performance from any one component in isolation, but combining them requires trade-offs in order to obtain the best system performance. At Spectrum, we specialize in making it all work together, looking at the bigger picture of board level and system level considerations for SDR. So here are some things to keep in mind when using and selecting a fast ADC. First, the ADC sample clock and clock distribution chain must be very clean, and clean in several ways. The clock needs to have low jitter, also measured as phase noise, and as Mark mentioned, the jitter requirement gets tighter as the input frequency and hence the slew rate increases. It's part of the price you pay for wide bandwidth. Clock spurs will also show up in the digitized signal from the ADC and may interfere with desired signals. You saw one slide that Mark had on that. You want your clock and your frequency reference to be very clean and free from spurs and noise. Second, frequency planning. You need to optimize the IF frequency and bandwidth with the sample rate. These must all be considered together. So a higher sample rate isn't always better. You need to suit it to the signal of interest and then select where your aliases appear. In this case, the signal of interest is your IF frequency. You don't want those signals to overlap. Now, a fast ADC's ability to operate at a high sampling rate and operate with a wide range of sample rates helps you to do this. Next, you need high-quality analog filtering. Filters remove noise and other undesired signals by removing the frequencies you don't want. Many key performance characteristics are a result of your filters that go before the ADC. Careful analog and digital design practices also drive performance. These practices include shielding and grounding. This impacts the design of boards and the metalwork for shielding. In the picture on the top right, you can see these example boards have many compartments that are separated from each other by shields to prevent cross-coupling of noise and spurious signals between the different sections of the board. Physical separation of the analog and digital components helps reduce the interference from the digital section into the analog section. And careful routing of clock lines is very important to avoid providing an easy path for interference between sections of the radio. Clock lines run all over your system, so just running a clock line too close to either a sensitive component or a noisy area of the system, or even too close to other lines, can let noise and spurs get into your signal. Your power supply can generate noise that can interfere with signals, especially switching power supplies, so you'll need to have good power filtering and possibly shielding around the power supply for radiated emissions from the power supply. Finally, the chassis provides the environment that your receiver lives in. Chassis considerations include shielding boards from outside interference, noise from the power supply and fans, temperature control, and the routing of the wiring. So what does this look like in the real world? Here's one example of a real-world implementation. This is Spectrum's RF4902 blade, and the boards on the previous slide were from that blade. It's a wideband RF transceiver which digitizes 195 megahertz of bandwidth in the range between 200 megahertz and 2.7 gigahertz. This allows subsequent digital processing of multiple channels or signals. It uses Intersil's ISLA 214P50 ADC, sampling at 490 megasamples per second at 14 bits. We selected this ADC because it offers a higher sample rate than any other 14-bit ADC currently available, and also it consumes less power than others in its speed range. The board also has an Analog Devices AD9122 dual DAC, sampling at 980 megasamples per second at 16 bits, and that enables us to transmit signals up to 400 megahertz wide. It uses Xilinx Vertex 5 FPGA to do the digital IF processing, and much of the signal processing that would previously have been done in the analog domain is done here in the FPGA. There's enough room here to do digital up and down conversion, along with other processing that's suited to implementation on an FPGA. It's frequency agile in the RF stage in the analog domain to enable hopping outside of the digitized bandwidth. This RF to digital baseband card fits in a 3U compact PCI slot. So for us, integrating the RF, the ADC, and DAC, and the FPGA all onto one blade helps us to optimize the system performance, including control of noise and spurious, clock jitter, and distortion. We mentioned that the, next slide. We mentioned that the RF40902 uses a high IF receiver architecture. That was the last architecture that Ed mentioned. And that allows us to simplify the receiver by doing more of the processing digitally. This provides a number of benefits. First, a small footprint with reduced size, weight, and power consumption. You can see in the picture the analog conversion module is about the same size as the credit card that it's laying on top of. Having a high analog bandwidth enables us to have a selectable IF frequency and IF bandwidth, so you can actually move that around, the IF frequency. And the high bandwidth also enables us to implement frequency hopping in the digital domain within the digitized bandwidth. We also get high dynamic range and greater flexibility by doing more processing in the digital domain. Let's have a closer look at the overall RF40902 blade and how it maximizes the advantages of the fast ADC. You can see on the block diagram that the RF40902 uses a modular design. The different colors are the three boards containing the RF section, the digital section, and the analog conversion section, which has the ADC and DAC. That's the green one in the middle. This helps provide isolation between sections to reduce noise and interference. This also helps with customization that helps us for future applications, because we can change the frequency range, for example, by changing just the RF transceiver module while leaving the other modules unchanged. So let's walk through what happens with a signal as it passes through the system. On the upper left, we start with a wideband high linearity low noise amplifier, LNA, followed by an external filter loop, which lets users select a filter or switch bank of filters that suits their specific application. We use dual local oscillators in each of the transmitter and receiver sections to facilitate fast frequency hopping in the analog domain. So having 2 for the transmitter and 2 for the receiver lets them operate independently. The receiver does a single down conversion of the signal in the analog domain with the high IF architecture. We use the high linearity analog stage for a high instantaneous dynamic range to ensure that the analog front end is not saturated before the signals even get to the ADC. In addition to high instantaneous dynamic range, there's a wide range of receiver gain adjustment. This enables automatic gain control to provide the ADC with signal levels close to their optimal levels. It has an ultra-low jitter clock generation circuit close to the ADC and DAC, and this is critical when you're operating with high frequencies entering your ADC. The second down conversion stage, including most of the filtering, is done digitally in the FPGA. This allows the user to select the IF frequency and bandwidth to suit the signal environment. It also has a high-speed serial interface from the FPGA to a digital baseband processor card, which is not shown here. The transmit path uses a 0 IF configuration with the dual DAC transmitting both I and Q. The 0 IF configuration gives the advantage of avoiding the image frequency, that's the difference between LO plus IF and LO minus IF. That's avoided in the transmitted signal. The 0 IF architecture lends itself a bit better to transmitters than to receivers, but it does require some careful balancing of gain and phase and DC offset for I and Q. Software-based compensation is possible, and we actually provide a facility for that with the board. Next, I'd like to talk about some processing that has been moved into the digital domain after the ADC. A digital down converter is used to perform frequency translation or mixing in the digital domain. Its functionality is equivalent to the second mixer stage of the super heterodyne receiver that Ed showed. DDCs are not new, but they've evolved over the past few years to get faster and more computationally efficient. A decade ago, DDCs were often ASICs, but nowadays the DDC is often in an FPGA in most SDRs. The local oscillator is replaced by a numerically controlled oscillator, NCO, also called a direct digital synthesizer, or DDS. We use the quadrature NCO to provide both sine and cosine signals to the mixer. The mixer uses multipliers in the FPGA to mix the incoming signal with the sine and cosine signals from the NCO. This separates the signal into in-phase and quadrature components, or I and Q, for complex baseband. The NCO runs at the IF center frequency, so that the desired frequency, or center frequency, is mixed down to 0 Hertz, or complex baseband, with I and Q. Digital filters are then applied to select the band of interest. You can isolate a single channel, or the DDC can provide a wideband output from which multiple channels can be selected with more digital filters located downstream of the DDC. Digital down conversion provides several advantages. The signal processing is flexible. For example, the channel filter's bandwidth and stop band can easily be modified for different signal requirements. For example, in a 4G LTE system, they use several different bandwidths ranging from 1.4 to 20 gigahertz, or 20 megahertz rather. Digital processing makes it easier to deal with different channel bandwidths and modulation formats with the same hardware. A second advantage of a DDC is precision. For example, the NCO's frequency resolution. This NCO that we're using can be tuned to a resolution in the thousandths of a hertz. The NCO's sine and cosine have precisely 90-degree phase offset from each other, and that's difficult to achieve in the analog domain. Mixing in digital multipliers has the advantage of linearity over a wide range of signal levels, whereas analog mixers have nonlinearities and can contribute distortion in that way. A DDC in this case is provided with the RF4902, and it's part of our software package, which we call QuickCom. It uses dual phases, or odd and even, in parallel. The ADC sample rate is too high for the DDC to process all the samples sequentially, so we have to break them up and use parallel techniques to run them through the system. It uses a polyphase filter with an integrated fractional resampler that has the advantage to give you almost any desired output sampling rate, including fractional rates. The DDC is implemented using model-based design using Simulink and Xilinx system generator, and that helps us to make it user configurable so you can modify it to suit the application. It also makes it easy to control from the software library. After the DDC, the signal gets sent onwards to baseband. It's actually a baseband signal that you can use onward to baseband processing either on the FPGA or further downstream in a separate baseband processor. That's as far as we'll take the signal processing chain today in our real-world example. So now I'd like to summarize what we've talked about today. Many applications can benefit from an SDR that has wide instantaneous bandwidth, high dynamic range, and small size, weight, and power consumption. These applications include things that are small and go fast, things that are portable, things that need to observe a large amount of spectrum all at the same time, and things that need to be future-proof by having flexibility. A high-speed, high-resolution ADC can help get you where you need to go by providing more flexibility. They also have the ability to simultaneously monitor more spectrum. They give you a higher sensitivity, and they can help you adapt to different signal and waveform requirements. They also simplify frequency planning, since signals, harmonics, and their aliases can be separated more easily as they appear further apart in the output spectrum. We've reviewed a real-world SDR platform that uses a high-speed ADC and some of the considerations involved in implementing that. Software-defined radios are challenging. There are many conflicting requirements that require good trade-offs. In the real world, no single design exists for all cases, but a flexible SDR can help provide many benefits in many cases. Proven platforms like the RF4902 blade can help reduce risk and speed your SDR system development. Now I'll turn it back to Lee to field some questions. Thank you.
Thank you, Tudor. So again, a reminder to everybody, if you have a question, please type it into your questions window, or else at this point, if you raise your hand, I can unmute your microphone so that you can ask a question directly. First question we've received for the panel is, why spectrum always starts with 9 kilohertz? Why not below that? Is there any specific reason for this?
This is Mark. And basically, you could start the spectrum lower than 9 kilohertz, but you really run into the audio frequency range there, and the usefulness of that spectrum is pretty limited because the wavelengths are so long.
Thank you. Are there any additional questions? So there's no questions that have been submitted. We can, oh, here we go. I'm being told to wait. Okay. Where will the slides from this presentation be available? I'll show the link for that again, but if you go to the Wireless Innovation Forum's homepage, www.wirelessinnovation.org, and click on tutorials, presentations, and webinars, the link for the slides will be available there. And it looks like someone's typing a question in right now, so we'll give them a moment to type. Question's been submitted. To what level of amplitude will the jitter impact overcome the noise floor?
To what level of amplitude will the jitter impact overcome the noise floor? Basically, the relationship will be tied to the thermal noise of the ADC and the jitter noise. So these noise components are summed together in a root sum of squares method. So you would take the square of the jitter noise and the square of the thermal noise, take the square root of that value, all in linear, not dB, and that would give you the combined SNR. So if the jitter noise and the thermal noise are equal, then the SNR would be degraded by 6 dB because those two noise terms would sum, and you would lose 6 dB of total SNR. So generally, a rule of thumb is once the input signal is below maybe minus 10 to 15 dB, below full scale, with a pretty high quality clock, the jitter impact is not going to be hurting you. But there are tables in our data sheets that show that as you increase the input frequency, depending on the jitter, that will limit your SNR. So there's a plot with diagonal lines that show the limit in SNR for different jitter values. And so if you had an ADC with an SNR of 72 dB, then you would follow out that 72 dB line until you hit the diagonal intersecting line that says, okay, at 140 megahertz, just make up a number, 1 picosecond of jitter is going to start to degrade your SNR below 72. So there's charts in the data sheets that show that. Does that answer the question?
Okay, the next question, why did you not use an ADC in your receiver?
We're actually not excluding the use of ADC from the receiver, but when you're measuring the instantaneous dynamic range, you want to know what your instantaneous dynamic range is before any ADC kicks in to change that.
Okay. Next question, what is the power consumption to different sampling rate? What is the power challenge to handset SDR implementation?
The sampling rate on a pipeline ADC, these high-speed ADCs, there's a certain amount of base power because you have to power different functions in the analog domain all the time, regardless of sample rate. and then there's a fraction of power that is related to the sample rate. So like the digital outputs of an ADC, the power will scale linearly. So if you double the sample rate, that output power requirement would double. And so the femtocharge technology that was mentioned earlier that Intersil uses eliminates a lot of the amplifiers or the high power pieces in the ADC and reduces that base power load to a very low level. But still, you would see maybe a 25% variation in power from the maximum sample rate to the minimum. So it's important to pick, the lowest possible power, base power ADC if you're targeting a portable application.
Okay, the next question we've received. Earlier in your presentation, you described how one parameter, possibly SNRO related, is improved by removing one part. Can you review this again?
I think I mentioned that the jitter degradation by SNR, or jitter degradation of SNR, can be, that situation can be improved if you use a lower jitter clock. Is that the reference? I think it would be this slide here, basically. Go forward one more, Ed. I think this is the reference, but I'm not sure. Where basically I stated that by reducing the clock jitter, or by getting a better clock source, that its impact on jitter would be reduced and would increase the receiver's sensitivity. And I would note that the slides include all of the speaker notes on them. So if you get a copy of the slides, then a lot of the additional details that we've talked about would be, covered there again. And certainly, if you have other questions, definitely send us an email or get in contact, and we'll be happy to, to go into more detailed discussion with you.
The person who submitted the question said, "Thank you, they will do that."
Okay, that'd be perfect.
We received one comment. Could mention the clock phase noise is termed reciprocal mixing in analog receivers.
I'm not sure I fully understand the question or the comment, but definitely there's a lot more to be said about clock phase noise and the sources of the phase noise and how that is integrated to create jitter. But in the limited amount of time, we were struggling to make sure we covered a fair amount of technical detail, but didn't run like maybe a day or two over our time limit.
Okay, we've got time for one more question, if there are any more. Okay, it looks like that's the last question. So if there's no other questions, then I'd like to thank everybody for attending the webinar today, and a special thanks to the presenters. I know it takes a lot of time to pull these materials together, so thank you so much for pulling this together and sharing with the audience. Again, a reminder to everyone that the satisfaction survey for this webinar can be found at the link shown on the screen now, and we'll send this link to everybody who attended so that they can provide us feedback. We really look forward to this feedback to help us improve these in the future. The next webinar that the forum we'll be running in our webinar series is entitled Cognitive Radio Network in the ISM Band, and this is going to be presented by Dr. John Sider of CRC in Canada. We'll be sending out additional information on how you can register for this webinar in the next couple of weeks. And with that, I'll close the webinar down and thank you everybody for your attendance. Thanks everyone.